So in a previous example video, we found the Maclaurin polynomials for f of x equals cosine x from order x equals 0 to order n equals 0 to n equals 6. Now I want to build off of that and try to write the infinite power series, so the Maclaurin series, generated by that cosine x function. Okay, and using patterns that we identified when finding this order 6 polynomial. So I went ahead and wrote down the P6 polynomial that we found in that previous example. Now, I've also written the first few derivatives for this cosine function. Notice that, so as you differentiate, I come back to cosine x at the fourth derivative, and now it's just going to cycle through. So the derivative of cosine is negative sine. And then we're going to cycle through these same four functions over and over. So we're going to cycle through these same values over and over in that infinite sum. So the Maclaurin series is, so it's the original function evaluated at the center, plus the first derivative evaluated at the center over 1 factorial, which is 1, so I don't really need to write that, x to the first. And then second derivative evaluated at the center over 2 factorial x to the second. Okay, and then you get the idea. So third derivative and so on. Okay, like I said, we already filled this out in that previous example up to n equals 6. So f of 0 was 1 plus f prime is 0. So this whole term here is going to be 0. F double prime was negative 1, so minus 1 over 2 factorial x to the second. F triple prime is 0, so the whole n equals 3 term is going to be 0. Fourth derivative is 1, sorry. So this is 1 over 4 factorial x to the fourth, and I know I'm rewriting what I had up there, but I guess I might as well talk through it. Fifth derivative, so n equals 5. So here's cosine. We're going to go up to sine here. So the n equals 5 term is just going to be 0. 0 times x to the fifth. Okay, but so that's still 0. X to the sixth, or the n equals 6, will be at this negative cosine function. So minus x to the sixth, there it is, minus x to the sixth over 6 factorial. Okay, so that's where we got this. Now, if you identify the pattern, I'm going to get rid of the zeros and just copy down what we had up there, which is maybe what I should have done in the first place, but okay, so we've got 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial. Okay, so if you had to guess the next term, and here's what you want to do. You want to generate these terms until you're able to guess the next non-zero term. So notice it's alternating signs. So positive, negative. So we expect the next one to be positive. We're only hitting the even powers of x. So I would expect the next power of x to be x to the 8th over, and whatever power of x we have up here, we have that factorial in the denominator. So it looks like I would guess that that would be the next term. Once you're able to guess the next non-zero term by identifying a pattern here, then you may be ready to write the sigma notation for this sum. So if we want, well, first of all, it's alternating signs. So we know that a good way to have this thing alternate sign is that negative 1 to the n. Because we recognize that back from when we studied alternating series. Okay, and then we want only even powers of x. So a way to generate only even powers would be to write this as x to the 2n. And then over whatever this exponent is, we want the same expression in the factorial, in the denominator, because these numbers always match, 4, 4, 6, 6, 8, 8. I want to have this sum start at 0. That way I get a first term of 1. And let me make that argument. So negative 1 to the 0 would be 1, times x to the 0 would be 1. 0 factorial is defined to be 1. So when n equals 0, you get 1 here. When n equals 1, we'll have negative 1 to the first, so minus x to the second over 2 factorial for when n equals 1. When n equals 2, we should get this term here. Let's see. Negative 1 squared would be positive 1. X to the fourth, 4 factorial. Yes. Yeah, so this expression right here is going to generate the terms that we want to see in this series for cosine of x. The sigma notation is nice, though, because that explicitly describes every term from 0 to infinity. So this would be our final answer for the Maclaurin series generated by f of x equals cosine x.